How sad are you? Or I guess I should say, are you as sad as I am that it's our last day of material? What? It is? It is. Because on Wednesday, I want to do a final exam overview. We won't really have time to do any review questions because there's not that much time. I'll kind of pick and choose some. But just before we start regression, which I am assuming that you've done lab 9, the linear regression or the introduction to linear regression lab, which is kind of a weird way to do it, but it's the only way that we can kind of smoothly get through the rest here. And regression is kind of a fun way to end the course. It's the line of best fit, y equals mx plus b stuff, right? And so just before we start, there were 2 versions of the test, and I want to thank you all for not cheating. So that's nice. And I know what you're wondering. Well, Emily, was there a significant difference in the average grades of the 2 versions? I'm glad you asked, because I did test your hypothesis. And what did I find? Well, first off, my null hypothesis is that they're the same. Average grade of version 1 is the same as version 2. In this case, this is one of those cases where I'm really hoping that's true. Otherwise, I'm in trouble, right? I did a 2-sided test because I don't care. I just want to know if there's a difference between the 2. Dun, dun, dun. What's the p-value? Skipping steps. We're there now. The p-value was roughly, wait for it, 0.4. Phew. Right? 0.4 is definitely larger than 0.05, which means I do not have enough evidence to reject H0, and I can breathe a sigh of relief. So the means or the average grades in the 2 versions were not significantly different. In fact, the average was roughly 62% overall. I want to say, I can't remember. I usually don't report the average because what should we be talking about instead? Well, what was the shape of the distribution? And if it's normal, we can talk about the average. If it's not normal, then we need to talk about the median. Anyways, but I know that someone's gonna ask, and so it was roughly 62%. So it wasn't the greatest test for anyone. Well, generally. So it feels like a good time to remind you that we had 2 tests, right? Still got our final exam. Now, as long as you do better on your final exam, so all I care about is you're improving, I'll shift the weight of one of your tests, so a lower test, to the final exam. Just one of them, but still, right? So you'll have another shot at it on the final exam. Yes, you're gonna have to do all these things all over again, right? So you'll have a chance to redeem yourself. And if it's better than, well, one of the tests, I'll pretend you didn't show up, and we'll call it a day. Shift it to the final. Yeah. You have to get 45 to be able to pass the course. So even if you have going into the final, thank you, that's something I forget to bring up, but it is important. So you do have to get 45% on the final to be able to pass. I think that's pretty reasonable. Basically pass the final, pass the course, but a little bit more lenient. Psychologically though, for me, pass the final to pass the course sounds way more reasonable than 45% for some reason. I don't know what it is. But for me, like 45, are you insane? 50, oh yeah, totally. I don't know, maybe that's just me. But you do have to get 45 on the final in order to be able to pass. Yeah. Nice. Okay, so we'll start regression. This is chapter 8. And I'm just gonna see how much damage we can do. You've seen some regression. You've used Excel to fit at least for his regression line already. You've used that line to predict things. So basically you've done everything that you could possibly want to do in this type of course. So that's got to feel good. But we're going to focus on some interpretation, the slope, the intercept, for example. And it wouldn't be a class if I didn't have a panicky moment. I am recording. Okay. And I'm not on mute. So that's a double win, I think. So we're going to be modeling numerical response variables. Okay. So remember, the response variable goes on your y-axis and your explanatory variable goes on the x-axis. Which means that you're going to use y to denote your response variable and x to denote your explanatory variable. There are methods for modeling categorical response variables, but we are only going to talk about numerical response variables because otherwise we'd have to get into logistic regression, which we'll save for a later course. How's that for a cop-out? We'll be able to handle numerical or categorical explanatory variables. So it's just the response variable that has to be numerical. So we can look at a scatter plot, which shows the relationship between two variables. Now we're gonna focus on two numerical variables in this case. And so it shows the relationship between high school graduate rates in all 50 US states and DC, and the percent of residents who live below the poverty line. And the poverty line in 2012 was income below $23,050 for a family of 4. And so now we've established what that is. And then we can figure out some percentage in poverty in each state. So each dot is a state. Each dot has some percentage of high school grads, X. So this means that X is the percentage of high school grads and Y is the percentage in poverty. Which means that the response variable, if I have the scatter plot, then I can figure out that the response variable must be on the y-axis. Then I look on the y-axis and I can say that it's the percentage in poverty. This is one of those scenarios where you might want to predict the percentage of high school grads depending on the percentage in poverty. There's no clear X and Y. So in this case, it's given to you like this, right? But what we want to remember is we use the response variable for the thing that we want to predict. Okay, so the response variable means that we want to predict the percent in poverty. In a different question, right? If I wanted to predict the percentage of high school grads, I would make that my Y. Okay? So we always want to predict the response variable. You had a little introduction in the lab where we talk about the relationship and fully describing the relationship by talking about 3 things. So the first thing that we can talk about is whether it's linear, right? We're just going to talk about linear versus nonlinear. Now, as a clue, we're only going to fit straight lines because we only have one day to do stuff. We can fit curved lines and stuff like that, but again, later course. And so you better tell me that it's linear, because otherwise, if you're telling me that a model like this would model the data well, then we don't have methods for that. Okay? And so for us, we're always going to say, it looks like I could fit some sort of straight line like this, and that models the relationship relatively well. So then I say it's linear. Okay? you don't want to be, this is like when we say the histogram looks normal, right? You want to be squinting. You don't want to get too picky because just overall here, looks like I could describe this with a straight line, right? So you don't want to get too picky. Oops. This line is either positive. So if it's positive, if it's a positive relationship, it goes like this. And if it's a negative relationship, it goes like this. In this case, when I look at this, I would describe that as a negative relationship. So far I have a negative linear relationship. Now, in terms of the strength, if you want to talk about strong or weak and nothing in between, right? Sometimes we put a little flair on it, like moderately strong, moderately weak. What does that mean? It means nothing to me, right? It's just kind of adding a little something. As a note, if you see any sort of relationship, I would say it's moderately strong to strong, right? So as soon as you see any sort of pattern, right? So here, when I look at this, as soon as you see some sort of pattern, you would call it strong or some version of strong, whatever you feel comfortable with. So as soon as we see a pattern, we can call it strong. And broad strokes, right? You're just kind of describing the relationship.
So if, could we interchange moderately strong and strong in this case?
Yeah.
Is it all about opinion, or is there a certain?
Yeah, depending on what field you're in, I know psychology like breaks it up into 0.1 intervals of the correlation, and there's different names that you're supposed to use if the correlation is 0.6 or 0.7 or something like that. I don't care, just go strong or weak, but I'm not going to get you to model anything that's weak because there's no point. There's no relationship. So I guess that's two gimmies. It has to be linear and it has to be strong. So then you just have to decide whether it's positive or negative. How's that? Because we wouldn't really model a weak relationship. If I don't see a pattern, there's no point in fitting a line to it. So then use Excel or other software to find the linear model, right? Which is what you did in the lab. And so here we can say, okay, this is your y hat. Now y hat, we've seen hats before for the sample proportion. Context is going to tell you that this is the predicted response variable or the predicted value of y. Which is the response variable. That was the goal of building this regression equation, is to be able to predict values of y. And so we've got this intercept. How did I know it's the intercept? Because it's not attached to the x. X in this case is the high school grad. Oops, different color. Let's do this. X was the high school grad. Let's start with the slope. The slope here is negative 0.62. Negative makes sense because I just said it had a negative relationship. So of course the slope has to be negative, and it's negative 0.62. The intercept, the y-intercept, is the value of y when x is 0. So that's where it crosses the y-axis. Now I feel like I want to add a page here. They do introduce it, but I'm impatient. So the hat, we use it to say that it's a predicted value or an estimate, right? And that's the same thing. Predicted value. So that's the reason we build this model, is so that then I could take some value of X and I could figure out what the predicted value of Y would be. We can eyeball it if we have the scatter plot and the line, but I want you to put in the value of X. Some things to make sure of is, for example, okay, the high school graduate rate in Georgia is 85.1%. Now, percentages are tricky, right? Because usually we convert them to decimals, right? 0.851. So to be able to figure out which, if I use 85.1 as my X or 0.851 as my X, you're going to go back to the scatter plot and look at the scale on the x-axis. Just make sure it matches. Here, 80, 85, 90, so 85.1 is one of those values. Whereas if you put in 0.851, technically correct, right? But then you'd be way off. You'd be over here, right? On the x-axis. So you want to make sure that you match the input type. So you take 85.1 as your X and just make sure you bed mass, right? 0.62 times 85.1 and then subtract that from 64.78. Sounds silly when I say it, but it happens. So then this is going to be the predicted percentage in poverty in Georgia. 0.018%. I guess this would make a nice segue into residuals, which is the next slide, but I just added a page because I wanted to talk about some stuff. But just for later, right, this is my predicted percentage in poverty in Georgia. But Georgia is one of the points on my scatter plot, and there is some actual percentage in poverty. Now, the difference between those two is what we call the residual. But before we get to the residuals, I want to talk about interpreting the slope and intercept of a least squares regression line. In terms of theory, it might be the most important thing that we do. And so that's why I want to shove it down your throats right away while you're fresh. And then she introduces it later, we'll kind of float through it. So if we have a least squares regression line, a generic one that looks like this, and I'm going to match the formula sheet. Oh, you know what? Way. I'll do one better. I'll bring in from the formula sheet. You won't need this on the final exam, but it's on there just in case. I did do it on one of the assignments, but I give you the formulas to use. But that's just for practice. So don't freak out about that. Don't freak out about it. Because I will give you the correlation in some way. We're not there yet. So on your formula sheet, last little bit on there. Can you believe it? We've done all this. Let's see here. Two-sided even. Wow, you got a handle on all that gibberish. Slowly but surely. Told you. Okay, so if we have a least squares regression line, y hat is b0 or b naught plus 1 b1 or plus b1 times x, then b1 has to be the slope, and I even guide you there, right, with the slope b1. Okay. So even if you don't have to calculate the slope, then if I give you the regression line, right, you can figure out that the slope is b1, whatever's attached to the x, if you're totally blanking, right? And so we're gonna have the slope b1, which is going to be the correlation r times the standard deviation of y divided by the standard deviation of x. Now, I would give you those three things. There's 5 things, but I would give you those 3 things, and you'll be able to solve for the slope relatively easily. Okay. The y-intercept, b0, relies on b1. So even though it's a little bit counterintuitive to solve for the slope first, you're going to need the slope here, right? And so then you have the average of the y's minus the slope times the average of the x's. So that's 5 things that you would need, or I need to give you, in order for you to build this regression line by hand. So I would say you're given the correlation x bar sx, which is the standard deviation of your x's, y bar, and the standard deviation of your y's. Which one you treat as your y's and your x is going to make a huge difference, right? And so you want to really establish which one is your y and which one is your x, because then that's going to determine your slope and your intercept later. But what did I want to do? I wanted to interpret. To interpret the slope, there's a standard sentence that I want you to use, okay, and you can apply it. And when it is standard like this, I do like to give you standard sentences. They sound a little bit funny. That's okay. You can just have it, memorize it-ish. And so to interpret the slope, which is b1, the slope is for each unit increase in x. Now that unit increase in x is really important. So for each unit increase in x, now you would substitute in whatever your x is, right? Percentage of high school grads, for example. Bless you. We expect a slope increase. And this is where slope, you would say b1, whatever it is, slope increase in the predicted value of y. And y would be the percentage in poverty in this example, right? So for us, what would it read like? It would be for each unit increase, in percentage high school grads, we expect a negative 0.62 increase, and this is where it gets a little bit weird. Now, if you're, feeling savvy, right, you could say a negative increase is a decrease, but then you'd have to drop the negative, right? That's important because a negative decrease is actually an increase. So you don't want to trip yourself up. So for me, I just always say the slope increase, so I don't mess it up. It's technically correct. Just sounds weird, right? We expect a negative 0.62 increase in the predicted percentage in poverty. it's this for each unit increase in X, we expect to see a slope increase in the predicted value of Y. Now you can let the formula sheet be your guide. And I know what you're thinking, is she ever gonna stop with that? No, I won't, because it's all there, right? If I look at Y hat is B0 plus B1X, and I wanna figure out what B1 is, then I can say, okay, if I let X go from 0 to 1, right, B0 just stays B0, then what happens? Then my Y hat increases by B1. For each unit increase in X, my Y hat increases by B1, right? How about the intercept, the y-intercept? Well, if we let the formula sheet be our guide, how could I figure out how to interpret this intercept? Well, I could let X be 0, right? Then the y-intercept is the predicted value of Y when X is 0. There. So now for the y-intercept be 0, the y-intercept be 0, and maybe I should use the same format. Sometimes the sentence structure doesn't work out, but the y-intercept of, oh, you know what? B0, let's do that, is the predicted value of Y, whatever Y is, when X, whatever X is 0. So in our case, what was our y-intercept? Our y-intercept in this case was 64.78. So my predicted percentage in poverty for a state with 0% high school grads would be 64.78%. We'll just take it at face value.
My stats didn't do good, eh?
Oh. Just gonna mute everyone just in case. You're allowed to unmute yourself, but it's okay. Okay. The y-intercept of 64.78%, I want to say. Yeah. Is the predicted percentage in poverty in a state with 0% high school grads. Now, the obvious follow-up is that meaningful? Not really. I mean, so here, this is where you would argue, well, a state with 0% high school grads, it doesn't exist, assuming we still go to high school and we make our kids go to school and all those kind of fun things. And so here, the follow-up, and I'll just put it on this page, hopefully I don't run out of room, is it meaningful? This is where you're going to argue, can X be 0? There's no wrong answer. There's a more correct answer than others, right? But what you're going to argue is, can X be 0 reasonably? So argue whether X can be 0. I'll say reasonably. If you tell me that, sure, a state could have 0% high school grads, and so to me that's meaningful, fine, that's fine, right? But you have to center it around X being 0, right? Because that's the definition of the, or that's the interpretation of the y-intercept. Another way that you could look to figure out if it's meaningful is, well, the domain, or sometimes I get lazy and I call it the range, which if you've done math, that doesn't make sense. But the range of our X values is between, looks like kind of 75 to 95-ish. So there is no value at X equals 0, right? And so I guess I'm giving it all away, but that's what we call an extrapolation when we're using this line. So lines continue forever and ever and ever, negative infinity, positive infinity, but we built this line off of just values between let's say 75 and 95-ish. So it's only reliable on that short stretch. Yeah? And that's, I guess, way later in the slides, but so that's the part. So interpreting the slope and interpreting the intercept, we didn't do in the lab, but you did find the slope, find the intercept, used it to predict values. I'll skim through the residuals, okay? But the residuals are the distances between the actual value and the predicted value. And so here on this line for this value, oh, kind of sloped, sorry. Let's do this. Y hat is 14. So the predicted value of y is 14, whereas the actual value of y, the y actual is 17 point something. So that distance is what we call the residual. Notice that they're at the same value of x. So that's how we can find them. I have this point in my data set, then I can use that same value of x to calculate the predicted value of y, and then I can find the distance between the two. I mention that because there's a question on your assignment where you have to do it. It's not something I'm going to get you to do on the final exam though, so that's why I'm get her out of here. So we've got the residuals, which are on your formula sheet. Where is it? All right, the residuals is the observed y minus the predicted y. Or we can use E for the error. Observed y minus the predicted value of y. And we can calculate these residuals. Now, in a kind of roundabout way, the residuals determine what the line is. Okay? And so that's how we find this line, is the least squared regression line. It's the line that reduces and finds the smallest sum of squares. So it kind of fits a line, calculates the residuals, fits the line again, adjusts, and it's kind of mind-boggling if you think about it too much. So we will not. We've seen the correlation, you've calculated the correlation in the lab. Now the correlation describes, and I'm going to add the strength and direction of a linear relationship. So you can calculate the correlation of a nonlinear relationship and it'll give you a value because it doesn't care, right? But it only applies if you have a linear relationship. And we take on, so the correlation is denoted by a lowercase r or sometimes a capital R, but I tend to use a lowercase r, although I think the textbook uses a capital R, which is confusing, but I just can't shake it. So the correlation goes between -1 and +1. So here, let's see here. Let's draw. Nope, doesn't keep going. It ends at -1, +1, throw a 0 in the middle. I'm gonna say anything roughly between -0.5 and 0.5, roughly, I'll consider weak. In fact, a correlation of 0 means there's no linear relationship here. It's just a cloud, and there's really, you can put your line anywhere and it doesn't matter, right? You're not going to be able to get any predictions. Whereas here, this is strong and positive because it's a positive value. Whereas here, this would be a strong negative relationship. Now, the strength is really just how close those points are together. Right? So we can do fun things like, okay, what do we have here? We've got a scatter plot. It's the percentage in poverty and the percentage of high school grads again. And we want to figure out what's the best guess at the correlation. You know? Now we'll do these relatively quickly. I know it has to be negative, right? Because it describes the strength and the direction. And so A and D are out immediately because they're positive. E is kind of staring me in the face because we just established that correlation has to be between -1 and 1. And so can't be -1.5, doesn't exist. So now my only two options here are -0.1, which would be no relationship essentially at all, right? But because I see some activity here, I can kind of squint and see some activity here. And so I'm going to go with -0.75. Yes. Can do the same thing. Kind of a weird data set. The percentage in poverty again, and the percent female householder, no husband present. Who cares? Whatever, it's a scatter plot. Can figure out a reasonable correlation. So again, I'm going to start with the direction. And if I had to kind of say any sort of relationship, I might do something like that. I would say it's positive. So that eliminates B and C. Then my go-to move is to check for anything outside -1 and 1. Okay. No such luck. That's all right. So we're choosing between 0.1, 0.9, and 0.5. Now, 0.9 would mean that these points make an obvious line, right? And so there's no obvious line here. I see some sort of pattern, broad strokes, right? But they're not all basically on the same line, right? And same thing with 0.1. If I'm saying it's 0.1, then it would just be a cloud, right? And there's no anchor. So for that reason, I'm gonna go with 0.5.
So the closer to 1 on either side is the more obvious the line is.
Yeah, so a correlation of 1, either positive or negative, is when every single point is exactly on the line.
Okay.
Yeah, which does happen in kind of a production scenario, right? I don't know. You give a machine some amount of material and it always produces the same amount, right? So then there's no variability. So it does happen, but there's a decoy in here. This right? We want to find which of the following has the strongest correlation. So the correlation closest to 1 or -1. And of course, this is a very, very strong nonlinear relationship. So what the correlation would do is it would fit a line like this and tell you how well it fit that line. It's not going to be very good, right? So even though you have a very strong relationship, right, the only places where those points are close to that line, which is going to result in a high value of R, is in these tiny little spots. Everywhere else, that line does a terrible job. So we would have a low correlation. So it's a strong nonlinear relationship. Whereas out of these remaining 3, this one, right, has the strongest relationship. Whee! And then I would, if I had to rank them, no one asked me to, I guess, but then I would go for D, and then I would go for C, because there's, if I squint, I could maybe talk myself into a relationship in C. This is 8.2. So how we fit our line, this is not something that we're going to concern ourselves with, but how we fit our line is we square the sum of the residuals, okay? And we use it because it's most commonly used, but we had other options, right? We square because we want to make negative values positive. It also amplifies large residuals, right? If things are far from the line, then that's bad. Just like in inference, when we were hypothesizing about the population means, right, or the population proportions, right, we had P's and we had mu's, and same deal, we're going to have some population intercept, right? We have a sample that we've modeled with this line, and so I model it with B0, my point estimate is B0, but really what I'm trying to model is beta 0. Okay. Same thing with the slope. I'm trying to model this population slope, beta 1, and I know what you're thinking, man, I wish we could do some inference on the slope to figure out if it's significantly different from 0. Well, surprise, we're not going to, but your Excel output does it for you. Okay, so that's what that p-value does beside your x coefficient. Okay. Let's see here. I'll just highlight the point estimates, because if you have a point estimate and the standard error of the point estimate, right, then you can calculate a test statistic, you can find a confidence interval, right? We're not going to do that, but we can. We had more time, but I never have time to get there. Like, oh, wouldn't it be so nice? Now, for the conditions, I'm going to go super fast because I'm not going to check the conditions for the least squares line on the final exam. But the first condition is relatively obvious. You have to have a linear relationship to be able to model it with a straight line. I think that's fair. We have to have nearly normal residuals. And so once you've calculated your residuals, which Excel or R or whatever will just do for you, then you can make a histogram of them and you can make sure that they look approximately normal. But you also have to have constant variability, which I'm going to show you. So the linearity condition, I think, is pretty straightforward. We can check things with a residual plot, which I am skipping. But if you ever see something like this, where you have the original scatter plot and then the residual plot down below, It's a way of assessing the line, okay? And in this residual plot here, this is the residual plot. You're looking for random scatter around 0, but that's not for us today. Constant variability. I want to show you. Yeah. Here, I'm going to give it away. This is violating. So if I have a relationship that looks like this is violating the constant variability condition. Okay? So we need to have even scatter around the line because, so here I'll highlight this constant variability, because otherwise this line does an excellent job predicting for a short amount of time, right? And so for values of X in this range, it does an excellent job it does an excellent job of predicting Y. But if we use that same line and that same correlation and things like that, what we're failing to mention is that kind of in this range here, it's doing a way worse job at predicting. So predictions are worse. So we need to have kind of an even spread around the line so that our predictions are equally reliable. On the final exam, I'll give you something like this. And so maybe in a sentence structure or something like that, but at its core, I have to give you 5 things, right? And I listed those 5 things already. And I might give you a scatter plot, which will give you the Y and the X, which value is your Y, right? This is your Y, and this is your X. Here, it's really explicit and it says it, right? That's not always the case. I might say the mean percentage of high school grads is 86.01% with a standard deviation of 3.73. Then it's your job to say, okay, X bar, because my percentage of high school grads is X bar is 86.01 with a standard deviation X of 3.73. So here, correlation is just using capital R, but I like little r, doesn't matter. So now, if I asked you to find the slope, then the slope is the standard deviation of Y divided by the standard deviation of X times the correlation. So if you have all those things, it's a simple matter of plugging things in. I wanted to use these values to highlight the importance of not mixing these up, SY and SX. Here they're relatively similar, so I guess you could maybe get away with it. It'd be weird, but you get slightly off values. But just make sure that you keep your SY on top and your SX on the bottom. The negative correlation is how we get that negative slope, right? That negative 0.62. Then I think usually I do part A, describe the relationship. All right, I give you a scatter plot. You have to talk about the shape of it, the strength, the direction, and then I give you the information that you need and I say, calculate the slope or find the slope. Once you've done that, part C, interpret the slope. Oh, dang it. For each unit increase in X, right, or for each additional percentage point in high school graduate rate, we would expect the percentage living in poverty to be now, so she gets fancy, right? But we could say we expect the slope increase, so negative 0.62 increase in the predicted value of Y, the predicted percentage living in poverty. That was part C. Part D. Find the y-intercept, or find the intercept. All right. The y-intercept from your formula sheet, I think these are the same, is the average of the y's minus the slope that you just found. Now, if for some reason you're unable to find the slope, I want you to just say, let the slope be 3 or something reasonable, right? -3, I don't know, right? Just if you don't have it and you need it later on, just give me a reasonable value for it and then just go from there, okay? And then you can interpret that. So even if you don't know how to find these values, you can still interpret it, right? Tell me that the slope is something and then interpret that. You could have canned answers. Just force the slope to be 14. Just memorize that. That's fine. It's not ideal, but I'm okay with it. So we take the average of the y's and the average of the x's. Now in this case, 11.35, if you swap that with 86.01, that's going to give you weird answers, right? So that's when you really want to keep track. And so that's where we find our slope, or sorry, our y-intercept of 64.68. And it's just where the line crosses the y-axis. In this case, it's not meaningful. I would say it's not meaningful because there are no states in our data set with a 0% high school grad rate.
We're supplied all of these, right? As in like the X bar,
yeah.
Y bar, and all that.
Yeah, and I'll give you lots of practice where it's in a sentence.
Okay.
Usually I'll do that. So you'll want to keep track of which one is your X and which one is your Y, and then just kind of sort them into something like this. And then, yeah, you'll have them.
Okay.
Yeah.
Sounds good.
Okay. So then you found your intercept. I forgot what part we're on. It's a many part question. Interpret the intercept. All right. The intercept, 64.68% is the predicted percentage in poverty for a state where there's 0% high school grads, right? Probably one of these. I don't care to read them all. So I'll just skip to the answer. D. States with no high school graduates are expected on average to have 64.68% of residents living below the poverty line. Right. And I would say, so here, often I'll have a question on, is the y-intercept meaningful? This is where you argue one way or another. Yes, it's meaningful because X can be 0, right? And the percentage of high school grads could be 0, right? Or no, it's not meaningful because in this case, since there are no states in the data set with no high school grads, the intercept is of no interest, so it's not meaningful. Not very useful, and also not reliable, since the predicted value of the intercept is so far from the bulk of the data. And I'm going to add, which we used to build the line. All right. The line extends because that's the nature of lines, right? They just go and go and go and go. So you can use lines to predict values outside the range of the data, but you shan't because it's called extrapolation, which is on some slide here. We've seen this. Here's our actual line. I think I had just drawn a fake line, probably pretty similar. So once you have your regression equation, you can use it to predict values of y. And so you plug in the value of x, which you can do by just eyeballing it. But I want you to use the regression equation. I want you to eyeball it though, so that you can make sure that your answer makes sense, right? So use it, but don't use it exclusively. So extrapolation is what I keep trying to introduce, and here it is when you are applying a model estimate to values outside the realm of the original data. That's when we call it extrapolation. Sometimes, well, one, the intercept might be an extrapolation. Sometimes it's our best guess, right? We don't have anything else, and so sometimes it's what we have to do. Okay? But in general, our predictions are not reliable when we extrapolate. When we predict within the range of the data, we call it interpolation. Okay, so interpolation, just as a note, this is where we have reliable predictions. And you can go a little bit beyond that, but you don't want to go too much beyond it, right? If you think about predicting someone's height based off of their age, and you've got their heights between the ages of 2 and 16, and then you're going to go and predict their height when they're 30 years old, what would happen? Uh-oh, that's bad, right? Because we're growing, and we have that understanding that, well, at some point we stop growing, so then the line becomes useless, right? Unreliable. Most of the time we don't have that knowledge about the data, right? And so that's where it becomes dangerous to start using the line to predict values that we haven't built the line from. So then, oh, that's just examples. So we can predict, we found the predicted percentage in poverty in Georgia, for example, way earlier. And so I can get you to do that, right? Use your regression line to predict for some value of X, right? And then I might get you to do it again and then follow it up with, do you trust this prediction? Usually that means, well, I know that means I've made you do an extrapolation, and the key word that I'm looking for there is, no, I don't trust it because I'm extrapolating. Okay. So good. Some examples of extrapolation. This isn't the craziest one. So we've got the year and then the men's age at first marriage. And so here they were quite, quote unquote, old. And then they got younger and younger as the years went on, world wars, etc. And so if we use this data to predict values here in, let's say, the 80s, 90s, and now, it would do a terrible job. This one is kind of crazy from BBC News. I can't believe this. And I'm sure they're just, why did we do that? So their headline is women may outsprint men by 2156. Wow. Crazy. You can read it all, but what was it based off of? It was based off of this. So we've got our data here. I'm guessing the red The men is in blue and the women's in red. How predictable. Pun intended, I guess. So then we've got our interpolation here, right? Times, winning times are lower, right, than losing times, right? And so you actually want a lower time. It's one of those kind of mind-boggling things. So we've got an R squared, which we've seen in the lab, but the R squared is the percentage of variability in Y that's explained by the least squares regression line on X. It's basically saying how well your line fits the data. So for an R squared close to 1 is a perfect model. And R squared is between 0 and 1. And it is the correlation squared, right? If you take a negative value, square it, becomes 0 and 1, which makes it a percentage if you wanted to. And so here, 78.9% and 88.2%, these lines are relatively strong. They're doing a good job of modeling these points. Let you think about what these lines are. Could they be confidence intervals? Yes, they can. They might be prediction intervals, which we're not going to talk about, but they're basically the same, right? So we can have confidence intervals around our slope and our intercept and our predictions. And so what happens as I move further and further away from the data, these confidence bounds are getting wider and wider and wider, right? To indicate that, I don't know, I didn't build anything off of these points. And so pretty quickly here, they start making a jumbled mess. And I guess at this point, this is what they went for. So weird. 2156, that's where those lines intersect. But there's a lot of uncertainty and a lot of mix and match there. So you just want to be careful. So R squared is the square. R squared is R squared. I use a little r, but then I use a capital R squared for R squared for some reason. You can use a lowercase if you want. So for me, R squared is the percentage or proportion of variability in Y explained by the least squares regression line on X. Now, because we haven't spent very much time on this at all, what I want you to do is as soon as you see either percentage of variability or proportion of variability, remember the 3 P's are the same, okay? So some fraction of variability, just stop reading. You know it's R squared, right? Let that be your trigger and just say, okay, all right, I'm gonna keep reading and confirm, but she wants me to calculate R squared, right? Which is just the correlation squared. Isn't it the slope? Well, I guess they're very similar because the standard deviations are so similar. So then 0.38 for R's, which means if I had to interpret, then 38% of the variability in percentage in poverty is explained by the least squares regression line on percentage of high school grads. All right, but again, percentage of variability. Nice. Gonna skip to the answer because we just did it. Just as a quick introduction, and you saw it in the lab as well, but if we have a categorical variable east-west, then what we can say is we can switch west on and off, and if west is off, east is on, which means that it's called a reference level, right? And so here, if west is 0, east must be 1. If west is 1, it's on, right? So it is west, then east is off, and you don't worry about it. We have a y-intercept. Okay. The y-intercept for the predicted percentage in poverty, presumably again, is 11.17, which is the predicted percentage in poverty when x is 0, which means that west is off, so east is on, right? So if we're in the east region or some eastern states. So for categorical variables, we call these dummy variables where they're on, off, on, off, on, off, zeros and ones. And you can make a series of dummy variables and have them represent different combinations, but nah, not for us. Again, many different dummy variables, right? Either Midwest is on, West is on, or South is on, but not all of them at the same time. Blah, blah, blah. But you always have to have a reference level. Very, very quickly about outliers. Eek. So outliers, we've talked about outliers a lot in the beginning of the course, right? And so now we want to think about if I fit a line like this, and if I really zoom in here, does this line do a good job of modeling the data? I would say not really, because it's being influenced by, should look something like this, if we didn't have these guys to try to capture, right? So that's the problem with outliers. Now it's tempting to just delete outliers, but here it looks like there is some phenomenon that's making this happen. And so that's usually the interesting part of our analyses. And so you don't want to delete those, but you might want to temporarily remove them and see how they affect your slope and your intercept, for example. There are different kinds of outliers, right? But overall, with outliers, if our data has outliers, we usually fit the model with all the data. Okay. We fit the model, which is the line, with all the data. Okay. Figure out what the slope and the intercept are. Right, find the slope and the intercept. Then I would remove outliers, kind of the most extreme ones, but incrementally remove outliers. Then incrementally remove outliers. Until there's no change in the slope and the intercept. And there might be some change, but no significant change until there is no significant change. And I know I said significant, so there must be a hypothesis test in there. You're absolutely right, but not for us. No significant change in the slope or the intercept, but usually we focus on the slope. Because you don't want to have outliers in there that are impacting your slope hugely. But if you're able to keep them in there and it doesn't impact your slope by very much at all, then you're better off just keeping them. Okay, so the overall goal is to keep as much data as possible. You might have extreme scenarios like this, where if you have outliers over here, right, then, and there's, you know, theory about, okay, if it's on the horizontal outlier, then it might be high leverage, blah, blah, blah. But don't worry about that. Just remember that outliers influence the slope of the line and the intercept. And so what do you do with that? You try to keep as much as you can, but in this case, you'd want to model these guys separately, right? You don't want to lump them in with these data points, right? Because if you fit the line with the outliers, that model is going to look like this. And that's not going to be very useful for any sort of prediction, right? Maybe over here. Whereas if you remove the outliers, then you get this general model that looks relatively decent. Skip this because we didn't talk about it. Nope. I wasn't gonna, well, I never thought I'd get this far. Just been motor mouthing. Should we call it? No. Inference for linear regression. Inference for linear regression.
How much more do we have?
I know, I set you up. I phrased it weird. Well, it's just a t-test, guys. It's just a t-test. If we have output like this, looks familiar-ish. This is our output, but Excel looks the same, right? We've got the coefficients, we've got the y-intercept, we've got our x value. So here I can build this line. I can say that y hat is 9.20760 plus 0.90144 times the bio IQ, knowing absolutely zero about this data set. Biological IQ, probably. The output gives you the estimate, which is the point estimate of the intercept and the slope, gives the standard error of each of those. It calculates the t, where the t is the point estimate. How far is it from zero, taking into account the standard error of the point estimate? That's a t. We know what to do with t's. We could use the t table. or Excel to find p-values. And so here, the key is from this 0, that means that I'm testing if beta I is significantly different, is equal to 0, or if it's significantly different from 0. This is obviously not something that's on your final exam, but it's fun to know because we know how to do these things. And so here, your two-sided p-value is 0.00080 and then 129, very, very, very small, telling me that the slope is significantly different from 0. That's nice. Therefore, the slope is significantly different from 0. A slope of 0 means no relationship. So then we can conclude that there is a relationship. But that's for another course. And you know what? With that, I thank you and I release you. There ends your stats journey, sort of. And we'll do final exam overview, review-ish on Wednesday. Stop this.